Hey everyone, back to a new awesome video, and today we're going to continue with our series about electricity and magnetism. Today we'll start a series of 2 videos about capacitors. First of all, we're going to introduce what capacitors is, what is capacitance, different units, etc. After that, we will treat 2 types of capacitors, parallel plate capacitors and cylindrical cells capacitors. So, let's start. Alright, from last video we examined conductors, and today they are going to be very useful because they are going to be the building parts of capacitors. If we have a conductor which has some charge Q, we know this conductor is going to be an equipotential. That is that every point on the conductor is going to have the same electric potential. We will call it B. And by all the rules we have been studied, we know that Q is going to be related by a linear relationship with the equipotential. Because if you have, we studied it, the potentials usually depend on charge and on degree 1. So we can relate these two quantities by inventing some variable, some new magnitude, we're going to call capacitance and represent it with a Z. And it's going to relate the voltage with the charge, the electric potential with the charge of a conductor. Now, it's important to examine what the units of this new capacitance are. So, capacitance in the SI units has the units of F, which is a farad. Now, by using this example, we can find exactly what those units are, as we know that the units of C are going to be the units of Q over the units of voltage. If you remember correctly, Q has the units of coulombs and volts had the units of joules over coulombs. So if we simplify this further, we're going to have a coulomb square over joules. And to express it in terms of initial magnitudes, we're going to have that this is coulomb square over kilograms, meters squared, seconds squared. And these are going to be the units we deal with when dealing with capacitance. This is a farad. Now, if you have 2 conductors, one with a positive charge Q and one with a negative charge minus Q, there is going to be some difference in potential between them. This is going to be a potential of V1 and this is going to have a potential of V2. And we know that the charge is going to be related by the capacitance of the whole system, not the capacitance of this one or this one, but the whole system, to difference of the voltages. So it's V1 minus V2. And the great thing about this system is that and why this is called a capacitor is because it's capable of storing energy. And we will use this kind of systems to store energy in a much more sophisticated way. Alright, one of the simplest versions of a capacitor, which is actually useful, is 2 charge parallel plates. If you remember from earlier, we found that Q equals the capacitance times the change in voltage. And actually this is going to be an absolute value because capacitance is always positive. Therefore, we're going to have that the capacitance is going to be equal to Q by the change in voltage. And if you remember from our past videos on electric potential, we found that the difference in potential of this situation is going to be equal to the electric field times the distance, which in this case, if you remember, this is going to be sigma, the surface density of each of these plates, times d divided by epsilon naught. Wait, now we know this is going to be positive, as we are going to take the positive value of sigma, positive value of the distance, because distances are always positive, and the epsilon naught has a positive value, which is measured experimentally. So capacitance is going to be equal to Q over epsilon d over epsilon naught. Sigma, and we call that this sigma times the area of the plate is going to be equal to the charge density, to the total charge. So we can write the total charge in terms of that sigma times the area of the plate, and this is divided by sigma d over epsilon naught. Now we can make some cancellations over here with both charges densities, and we end up getting that the capacitance of this object is going to be equal to the area of the plate times epsilon naught over d. And the capacitance is also a measure of how much energy can this object store. We will see in later videos how both quantities are related. And we could see that the farther apart the objects are, the capacitance is smaller, and the closer they are, the capacitance is bigger. Similarly, with the area, the bigger the area, the capacitance is bigger, and the smaller the area, the capacitance is smaller. This will correlate with the energy. However, as voltage will also enter, and it also depends on the distance between the objects, the relationship with the distance is not that easy between the energy and the distance. So we'll have to wait for the next video to see that. However, the important thing to take from here is that this is the capacitance of a system of two horizontal charge plates. Right, now let's treat another example of capacitor, the cylindrical cells capacitor. To deal with it, we will define a quantity, a charge density, a linear charge density of Q over L. And we found in our applications of Gauss law videos that the electric field in this case is going to be equal to the charge density divided by 2 pi r times epsilon naught in the r-height direction, and only in between both cylindrical cells. On the outside is going to be 0, and on the inside is going to be 0 too. Then we also found in our electric potential videos that the charge difference is going to be equal to minus lambda over 2 pi epsilon naught logarithm of b over a. Now that we have this information, we're going to be able to calculate what the capacitance is. Remember that Q equals Z times the change in potential, which we're going to take the magnitude of, and we will get that C equals Q over, canceling that minus sign because this is positive as B is bigger than A, and we'll get lambda over 2 pi epsilon naught logarithm of B over A. Now, we know that Q is over here, it's lambda times L, so we will repeat the same drill we did earlier, substituting lambda L up here and getting the lambda, the logarithm of B over A, and we will take this up 2 pi epsilon naught. Now we can cancel some of this, the lambda with the lambda, and we end up getting that the capacitance equals 2 pi L times epsilon naught divided by the logarithm we have over here, the logarithm of the ratio of the radius of each of the different cells. What we see is that the longer the cells are, the longer our capacitance is going to, well, the higher our capacitance is going to be. And also, we see that this logarithm grows whenever this ratio grows. That is, the more separated the two cells are, the higher this capacitance is also going to be. However, once again, as this is also a part of the change in potential, when translating it to energy, we are going to have different effects that we cannot figure out yet. That is all for today. I hope you got a sense of what capacitance is, and probably in the following video about capacitors you will understand it more. Also, we have explained 2 of the 3 basic capacitors, and I hope you understood where we got these capacitance values from. Any doubts left, you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!